Good afternoon, everyone. So, in today's lecture, we will discuss the design of truss girder bridges. This lecture comprises of two parts. This is your part one, where we will deal only the how to calculate the various loads on the members. And in part two, we will actually design those members. So, if you want to see the design of complete truss girder, see the video of both the parts. That is part one and part two. So, let us start here. This is my problem here. Truss girder through bridge is provided for single broad gauge track. As we discussed last time, that there are two types of bridges. One is deck type and the other one is through type. Through type bridge means the load is carried at the bottom chord level here at this level. Is provided for single broad gauge track. The track is single here. Okay. The effective span of the bridge is 50 meters. So from here to here it is 50 meter. The floor beams are spaced 5 meter apart. So these are the floor beams here. Okay. So these beams are spaced at a distance of 5 meter. The stringers are spaced 2 meter between center lines. And these are the stringers. This one. Okay. These are resting on these floor beams. Okay. So these stringers, the spacing between the stringers is 2 meter. And over these stringers, we have to provide the sleepers here at regular interval. And over the sleepers, we have to provide the railway track. Now, what is the next data? Next data is given as 0.6 kilonewton per meter stock rail and 0.4 kilonewton per meter check rails are provided. So the rails which are provided here for the movement of the traffic, the weight is given as 0.6 kilonewton per meter for stock rails and 0.4 kilometer per meter check rails. Sleepers are provided at 0.45 meter from center to center. So the spacing of the sleepers here, okay, these are provided at a spacing of 0.45 meter. The size of the sleeper is 2.8 meter long and 250 by 250 meter in cross section. Weight of timber of the sleeper is assumed as 7.50 kilonewton per meter cube. The main girders are provided at a spacing of 7 meters between their center lines. So this is main girder, this one. Okay, one girder here, another girder is there, this one, the last one. So the distance between this girder and this girder is 7 meter. Design the central top chord member. You have to design member in the central top chord here, as well as here at the bottom chord member. Okay, vertical member, this vertical member, and any diagonal member, either this one or this one. The bridge is to carry standard main line loading. You have to take the Fy as 260 MP. Okay. So let us start the design here. Now come to the preliminary design. So what is given here? Effective span is given as 50 meter. So you have to calculate the panel length of the bridge girder. Panel length means the distance between the main beams. Okay, main girders. That is your 5 meter. It is given. Therefore, number of panels is how much? Total span is 50 meter and spacing between main beams is 5 meter. So if you divide 50 by 5, so we had 10 number of panels in the bridge. Now spacing between the main girders is also given in the problem is 7 meter. Now first of all, I have to calculate what is the height of the truss girder. So as per this is the code IS 1915, that is a bridge code. Okay, so minimum height is given as 1 by 10th of span. You have to choose the height as 1 by 10th of span. So span is 50 meter. So this is the minimum height, that is your 5 meter. Okay. Now for economic consideration, the height of the truss will be taken as 1 by 7th of the span. So it is comes out to be 1 by 7 of 50, 7.14 meter. Okay. So I have to choose a truss girder of a height of 6 meter, which is in between this 5 meter and 7.14 meter. This is the consideration, minimum consideration as per the IS code, and this is as per economic consideration. So I have to choose a whole value here as 6 meter. Okay. So this is my preliminary design of the truss girder. Now next step is calculation of the loads. So first we'll discuss the dead loads. Now what are the loads which are given in the problem? Weight of stock rail per track per meter. Now stock rail weight is given in the problem as 0.6 kilonewton per meter. Okay, so this is for one rail. Okay, now track means two rails. Okay, track means two rails. So I have to multiply it by 2. So weight of stock rail per track means 2. So this is 1.2 kilonewton per meter. Similarly, weight of check rails again per track. So it is multiplied by 2 here. 2 into 0.4, 0.8 kilonewton per meter. Now weight of fastenings, you have to assume it as 0.2 kilometer per meter. This is as per past practice. We have to assume the weight of fastening as 0.2. Now weight of sleepers per track per meter. How much it is? This is the length of the sleeper. This is the cross section 0.25 by 0.25. This is the unit weight of sleeper material, that is the unit weight of wood 7.5 kilometer per meter cube. And you have to divide the center to center spacing of the sleepers as 0.45 meter. So this comes out to be 2.92 kilometer per meter. That is weight of sleepers. Weight of stringers per meter. Stringers are those beams on which sleepers are resting. Okay, so stringers per track, again it is assumed as 3 kN per meter. Weight of cross girders, that is your floor beams, again per track per meter it is assumed here as 5 kN per meter. Okay, now you have to consider the self weight of both the truss girders. So self weight of the truss girders are calculated by Fuller's formula. Okay, the formula is this one: 15L plus 550 divided by 100, where L is the span in meter. So span in our case it is 50 meter. So 15 into 50 plus 550 divided by 100. So this is 13 kilonewton per meter. So next I have to add all these dead loads here. So total dead load is equal to how much? This plus this plus this, and you have to add each and everything here. Okay. So this comes out to be 26.12 kilonewton per meter. These loads are come per track. Okay. So I have to calculate total dead load per truss girder because there are two trusses, one on the one side, one on the other side. So per truss girder means I have to divide this total dead load by 2. Okay, so this comes out to be 13.06 kilonewton per meter, and assume it as 13.1 kilonewton per meter. So this is the calculation of dead load of the truss. Now in step number 2, I have to calculate the live load. Now because it is a moving load, the train is moving on the track, so I have to apply the I have to use influence line diagram for calculating the forces in the members. Okay. So first I have to calculate influence line diagram for U4, U5. Now look here, this is my truss here. Okay, so every member, that is the top chord member, I denote it as U for upper, U1, U2, U3, U4. Okay, for lower members I have to choose the letter L, lower 1, lower 2, lower 3, and so on. Okay, so here U4, U4 means both are U, that means it is an upward chord. Okay, so this is my you can say I have to design a member in the central chord, so I have to choose this member U4, U5. So I have to find out what will be the force in this member, because the force in this member continuously changing as the train is moving from left to right. Okay, so I have to apply the principle of influence line diagram to calculate the maximum force in the member. So for calculating maximum force in this members, the load is acting at the opposite joint. So opposite joint for this member is this one, L5. So when the load is at L5, the force in this member will be maximum. So I have to calculate what will be the maximum force in this member with the application of influence line diagram. Okay. So what I will do, I have to make a section here, 1, cutting this one, this section, this panel. So when I cut a section here, first I have to calculate the reactions. Okay. So what is the reaction here? Now taking the moment about this point, that is the left hand support. Okay. So RB, this is my RB. These are the 10 panel points here. So RB into 10. Okay. So this force is in anti-clockwise direction. Okay. Now when the load is here, because I have to calculate the force in this member, so force in this member will maximum when the load is acting at the opposite joint. So unit load will be here at L5. Okay. So 1 into this distance, and this distance is your 5 panel points. So 1 into 5. Okay. So RB comes out to be 0.5. So therefore RA comes out to 1 minus 0.5, that is again 0.5. So both the reactions are 0.5, 0.5. Okay. Now I have to calculate, considering the stability of left portion of the section 1, I have to consider the stability of the left side and taking moments about this point where the load is acting here. Okay. Now please remember, here I have to use the method of joint as well as method of sections. Okay. Somewhere I use method of joint for calculating the force rate. Somewhere I will use method of sections. Okay. Now you know that in case of method of joints, if uh, arrow is pointing towards the joint, that indicates a compressive force. So here this arrow is pointing toward this joint U4. So this means that it indicates a compression here. Similarly, this again pointing to this joint, again compression. Here at L4, it is pointing away from L4. So this is your tension. This is away from L4. This is your tension. Now, there is a thumb rule that generally most of the members in the top chord of any truss are in compression. Okay. So all the top chord members are generally in compression. All the bottom chord members are generally in tension. That's why I assume this arrow towards this joint, compression here. And this I assume away from the joint. And the vertical members and the inclined members have both the things, that is both the tension as well as compression side. So we have to evaluate it. Okay. Now after this, when the load is acting at 5, okay, I have to consider the stability of the left portion 1, 1. So RA into 25. When the load is here, I have to take the moment about L5. Okay. So RA into this distance is your 25 here. So every distance from here to 5 meter, 5 meter, 10, 15, 20, and then 25. So RA into 25, okay, this is your clockwise. So this force F U4 U5 will be in the anti-clockwise direction. So F U4 U5 multiplied by this distance, that is your 6. Okay. So in this, I have to calculate F U4 U5 is equal to RA is 0.5. This is 25 divided by 6. So this comes out to be 2.08. Now the assumed sign I have assumed as a compression here, and this is again comes out to be 2.0. This means that it is a compressive force. Okay. So the force in this member is maximum when the load is acting at this joint. And how much is the value here? 2.08 plus sign, that is compression. Okay. So I have to join it with a straight line here and here. So this is my IL diagram for F, U4 and U5. Clear? Next, I have to calculate L4, L5. L means both are lower chord units. Okay. So here I have to calculate the force in this member L4, L5. Okay. Now the train is moving from here to here. So I have to consider the unit load at this point, this point, this point, this point. So I have to consider this at this point, that is your L4. Okay. And then when it is L4 here, first I have to calculate what is RB here, RA here. So this is my RB into 10 is equal to, when unit load is here, 1 into 4. Okay. So RB comes out to be 0.4 and RA comes out to 0.6. Next, I have to take the moment about U4. Now, force in this member will maximum when it is when you take the moment about the opposite point here. This is at the point U4. Okay, so I have to take the moment here RA into 20. Okay, so the distance from here to here is 20. RA into 20. This is my clockwise. So F L4 L5 L4 L5. This is anti-clockwise direction. L4 L5 multiplied by this distance. This distance is 6. Okay, so F L4 L5. So from this, F L4 L5 is equal to RA is 0.6, 20 divided by 6. So this comes out to be 2.0. I assume this as a tensile force, and here again it is comes as tension here. Okay, so this is my tensile force. How much it is? 2.0 when the load is acting at L4 here. Okay, so this is the maximum ordinate, so I have to join it here and here. So this is my IL diagram for L4, L5. Next, I have to calculate U4, L4. U4, L4. Okay, both the 4 and 4 are here, so this means that it is a vertical member. Okay, if suppose that here it is L5. Okay, so this means that U4, L5 means it is an inclined member. So considering the stability of the left portion of section 2. Now for finding out the force in this member, I have to cut a section cutting this member. So this member is now 2, 2. Okay. Now I have to consider, because this member this is my member. So first I consider the load as this point, and then I will consider the load as this point. Okay, because in this member maybe there are two things. Maybe tension first and compression later, or maybe compression first and tension later. Okay, so that's why I have to first calculate the apply the unit load at the point L4 here. Okay, and then first calculate the reaction. So these are my reaction values. Okay, then applying sigma v is equal to 0. My load is here. Okay, and apply summation of v is equal to 0. How it is? Ra upside, so this is my plus. Load here at the downside, so this is my minus. Okay, plus this is my force. I assume it as in the up, away from the joint. So this is F U4 L4 is equal to 0. So at this joint there are three forces. Okay, applying summation V is equal to 0. Ra plus 1 minus and F U4 L4 is equal to 0. So from this I can calculate this force here. So F U4 L4 is equal to 1 minus 0.6 is equal to 0.4. I assume the arrow here as away from the joint. Okay, so this is a tension, and so this one is your tension. Okay, so this is my ordinate here is 0.4 under this load. This is my tension. Next, I have to consider load at L5 here. Okay, so again calculate RB and RA. So both reactions are same, 0.5, 0.5. Then again applying the summation of V here. Now summation of V is equal to 0. RA upside. Okay. Now my load is here now at L5 and section is here. I consider the stability of left portion of section 2.2. Left portion of section 2.2. So the load is here. So I will not consider the one load here in the equation now. So RA upside, okay, plus this force, that is F U4 L4 is equal to 0. Okay, there is no unit load here. So this F U4 L4 is equal to minus RA, that is how much it is? Minus 0.5. Okay, so here I assume this as, look here, I assume this as away from the joint, that is your tension force, and the sign comes out to be here negative, that is opposite to my assumption. So that's why it is your compressive force. Okay, in the previous case this sign comes out to be positive, so that's why it is tension. Got the point? So here my assumed direction is tension and the sign comes out to be negative, that's why it is compressive. Okay, so this one is 0.5. This one is tension, this one is compression. Okay, so the force is changing from tension to compression between, in this member, between L4 to L5. Now I have to find out what will be the distance of this changing of force from tension to compression. I have to calculate this distance. How much is this distance? So I have to apply the similar triangle principle here. Okay, just consider this triangle. This one, this is my 0.4, this is my 0.5, this upon this. Suppose that this is my x. So this is how much? 5 minus x, because the distance between this and this is your 5 meter. So I have to calculate point of intersection at a distance from the left hand support. How much it is? This is my 0.4, This is my 0.5. So this upon this is equal to this distance is your x divided by this distance is your 5 minus s. So this x comes out to be, this calculate comes out to be 2.22. Now in this 2.22 is from here to here on. Now in this I have to add this much distance, which is nothing but your 20 meter. So plus 20. So this comes out to 22.22 from the point A. So the remaining distance, that is 27.278, is from B point, support B. So these are my distances. Next I have to calculate the ILD for U4 L5. Now here it is 4, here it is 5, so this means that it is an inclined member. Okay. So again, when the unit load is at L4, okay, I have to calculate the RA and RB first. Then I have to apply the stability of the left portion of section 1 here. Okay. So again, RA plus, load is here, it is your minus sign. Okay. Now this is my force. Okay, acting towards the joint. So this force, when you resolve in vertically here, so this means it's in cos theta. Okay, so F U4 L5 times cos theta is equal to 0. Okay, so RA plus in this side, 1 minus in this side, and this force in this direction will be F U4 L5 cos of theta. So F U4 L5, calculate cos theta from this triangle here, very simple. Okay, this is my 6 meter, this is my 5 meter, so this comes out to be 61. Okay, by Pythagoras theorem. So cos theta comes out to be under root of 61 divided by 6. So just put all the values here, you will get 0.5. Now I assume this towards the joint, that is compressive, and again the sign comes out to plus, so this means that is your compression. So this is 0.52 compressive force when the load is acting at the joint L4. Next, consider the load at L5. So again, RA, RB is this one. Okay, sigma V is equal to 0. Again, see here, this is my RA in this direction. Okay, now unit load is here to the right of this section. I will not consider unit load. Only this F U4 L5 times cos of theta is equal to 0. So this comes out to be this much. Okay, and finally this comes out to be 0.65. Now I assume this as a compressive force, but the sign comes out to be negative, so this means that it is your tension. So this is my tension. So this is compression and this is your tension. Again, I have to calculate what is the value here. Okay, so the same distances comes out to be here. This is as in the previous case, the same values of this distance. Okay, that is your x value from this side as well as from this side. Next, I have to calculate the force in the member due to dead load. Okay. Now I already calculated the dead load as 13.1 kilonewton per meter. Okay. Now I have to calculate the force in the member U4, U5. That means upper member due to dead load only. So how much is this? The force area of IL diagram. I have already plot the IL diagram. Okay. So I have to take the area into intensity of the dead load. So area of IL diagram will be a half. This is my base is 50 meter. Height of this IL diagram U4 U5 is 2.08 into intensity of the dead load. So this is my compressive force due to dead load. Clear? Next, I have to force in the member L4 L5. So it is a bottom chord member. So there will be tension. So this is minus sign here. Okay, half. This is my base. This is my height of the triangle, and this is your dead load. So this is your tension force minus sign. Next, I have to consider the force U4L4. 4, this means it is a vertical member. Okay, so in vertical member, the first is when we draw the IL diagram, the first is the tensile force and then is the compressive force. So this is due to tension. Half. This is my base 22.22. I have to calculate from the left support. 22.22. This is my height of this tension diagram. Plus this is compression half. This is base. Height of the diagram is 0.5 multiplied by the dead load. So this comes out to be 32.8 kilonewton compression. Next, I have to calculate the force U4L5. Okay, so in U4L5, the first one is your compression, then there will be tension. So this is my force due to compression. This is my force due to tension multiplied by the dead load. So this comes out to be tension here. So we'll see that uh, in top chord member, the force will be compression. As I told you first, the thumb rule is that all the top chord members are in compression, all the bottom chord members are in tension, and in vertical member and inclined member, both the things are there. But when you calculate this, for vertical member, there will be a compression, although small magnitude. And for inclined member, this will be a tension. Okay, although again is small magnitude. Next, I have to calculate the live load and impact load. So these are the two tables. These are the actually the one table, okay, which are given in IS code, IS 1915. Now, what is this? Equivalent uniformly distributed live load. As I told you in the last lecture, we discussed the theory of the Girder bridges. We have to calculate EUDLL on each track and impact factors for broad gauge bridges. Okay, so this is given in three. One thing here, one column is for bending moment, then other for shear force, and the last one for impact factor. Okay, so the first column is the span of the bridge. Okay, so my span of the, and there are two further columns here. This is ML means main line. This one is your branch line. Okay, for shear force, main line, branch line, and this is the impact factor. So my span of the bridge is 50 meter here. Okay, and my load for bending moment for main line is this one. How much it is 50? 4380. Just remember this value, 4380 kilonewton. Okay. So when we calculate the force due to live load and impact load, we have to use this table. For dead load, we have already calculated. For live load, this one. Okay. So when calculating the live load and the impact load, okay, so we have to use this table. Okay, so my length of the bridge is 50 meter, so this is my value here. Okay, now for top chord and the bottom chord members, which are top chord member are generally in compression and bottom chord member are generally in tension. So we have some type of, you can say, the beam behavior is there. So the bending moment governs in the top chord member and the bottom chord. So for calculating the live load for top and bottom chord member, we have to look for in the column of bending moment. For vertical and inclined members, we have to look for shear force. Okay, because shear force is maximum in those members. Now I have to calculate the force in the member due to live load and the imposed load or the impact load. Okay, so first we calculate the U4, U5. Length, loaded length is how much? 50 meter. Now I have to calculate the impact factor. Impact factor means due to impact load when the train is moving on the track. Okay, so we have certain vibrations out there. So due to these vibrations, we have to incorporate a load that is called dynamic factor of the impact factor. So what we actually do, we have to increase the live load by a certain factor that is called your impact factor. This is the formula for impact factor, and it is also given in the table. So this comes out to be 20 plus 14 plus L span is 50 meters, 0.313. Okay. Now from bridge rules for broad gauge 50 meter loaded length, live load plus impact load per degree will be how much? This is my live load. So full live load will be considered. This is my impact factor. So live load is increased by impact factor into 1 by 2 of 4380. This is my load for bending moment. Okay, for a span of 50 meter. Okay, now why I will divide it by 2? Because it is your per girder. Okay, there are two girders. So for per girder, I have divided by 2. So this comes out to be this value. Now, this is the theory which I just already explained it to you. Okay, so nothing is I will discuss again here. Therefore, force in the member due to live load and impact would be how much? Area of IL diagram into intensity of live load and impact load. So how much it is? Area of IL diagram half. This is my base. For top chord member, this is my height of the IL diagram into intensity of live load will be how much? This is my total load divided by span of the bridge. So I will get a UDL type of thing here. Okay. So this is your intensity of the load in kilonewton per meter. So this comes out to be, this is my value. This is your compression. Next, I have to calculate for the lower cord. Again, loaded length is 50 meter. Impact factor remains the same. Okay. So I have to calculate the live load impact load. Again, same value as I calculated in the previous step. Now I have to calculate the force in the member. Because this is your bottom cord member, so 4 will be tensile, so this is minus sign. So half, because of half, sorry, the area of the triangle half base. This is the height of the aisle diagram 2 for bottom cord member. This is my load divided by 50 for UDL type of thing. So this comes out to be minus this value. This is my tension. Okay. Next, I have to consider the U4 L4. That is my vertical load. Now for tension, for this member, first is the tension and then is the compression. For tension, loaded length, we have calculated already this length, 22.22 from left support, that is your support A. Okay. So you have to calculate the impact factor for this much loaded length. For this much loaded length. So 20 divided by 14 plus L is 22.22. So this is your impact factor. So live load plus impact load per girder will be how much? This is full live load plus impact factor into half of this value. That is 2404.4. Now this is taking from the table corresponding to this loaded length 22.22 meter. Okay, and because this is your vertical member, so I have to choose the value, this value from shear force consideration, not the bending moment. Bending moment consideration is only applicable for top cord and bottom cord. Okay, for vertical member we have to look for the shear force. So this is the value of the shear force column corresponding to this much loaded length. So this comes out to be this value. Next, due to live load and impact load, how much it is? Minus sign because of tension, half base. This is my height. This is the load divided by this is the length. So this comes out to be tension. Next, for compression, loaded length is this much. Okay, impact factor is this much. So live load plus impact load part will be how much? 1 plus impact factor. Okay, 1 by 2 into this is my load corresponding to this much loaded length from shear force consideration. So this is my value here. Okay, so I have to calculate the force in the member is how much? Half base into height into convert this into UDL. Okay, this divided by the loaded length. So this comes out to be this much. Next is member U4L5. That is your inclined. Again, in this member, the first one is your compression. The loaded length is this much. I have to calculate the impact factor. Then I have to calculate the per girder load. Okay, so 1 plus impact factor half because of there are 2 girders. So this is my load. Okay, then force in the member due to live load and impact load, as in the same previous step, previous slides. Okay, half base height. You have to convert into UDL. So this is my force. Then for tension, my loaded length is this one. Again, using the same principle as in the previous slides, I have to calculate the impact factor. Then I have to calculate per girder, okay, force. Then I have to calculate the force here, okay, half base height, and this is my UDL. So this is my force, okay. So next come to the design force. I have calculated all the forces due to dead load, due to live load and impact load, okay. Then you have to calculate the design forces. Now look here. These are my members. U4, U5 upper member, this is my lower member, this is my vertical, and this is my inclined. The first column is due to dead load, second column is live load plus impact load, and the third column is combination of dead load plus live load plus impact load. So for dead load, you will see that because this is your top cord member, only compression is no tension. Then for lower cord member, no compression, only tension. Then for vertical member, we have in the dead load, we have compression force, okay, and for this inclined member, we have the tension force. Now come to the second column. Because it is your, you can say that again top cord member, so only compression, no tension. For bottom cord, no compression, only tension. For vertical member, we have both the things, compression as well as tension, but compression will be more. Okay, so these values show that compression will be more. For inclined members, the tension will be more. So here this value is more. In the next, I have to sum up all these things here. So this plus this, I have get this value. This is my total design force, that is the compressive force. Okay. Now here for this bottom chord number, this plus this, I have this tensile force. Okay. Then this is my compression. This is my compression. Okay. So this is my compressive force, and this is my tensile force. Again, this plus this, my compression force, and this is my tensile force. So this is all about the how to calculate the various forces in various members of the truss. So this is the first part of this problem. Uh, in the next lecture, we will design those members. That is, these members uh, corresponding to these forces. So I have to design this members using this compressive force. I have to design this bottom chord member as a tension member using this force. Okay, and similarly I have to design this member and this member considering this compression and the tensile forces. So for the design of these members, please see the second part of this lecture. Thank you so much.